Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to really pick up where we left off last time, talking about how we can look at non-ideal systems. And we're going to use a fair number of properties to try and do that today. So last time we built up our new general relationship for the change in internal energy in terms of volume and temperature. And doing so, we generated this idea of the internal pressure, which is really going to stand in for the intermolecular forces and how changes in volume can change that favorability of the system. Now, one of the things that we can do is we can use this as a starting point to look at how the internal energy changes with temperature under isobaric conditions and not just isochoric. And we can do this by dividing all three of our terms by dt while holding pressure constant. So again, this just gets us the change in the isobaric change in internal energy for the first term. But we also get a very useful property on this second one, the isobaric change in volume. And then the third term is just the change in temperature with change in temperature. So this last term will just go to 1, and that will help simplify the system. So now we've got really two unique derivatives. We've got this isobaric change in temperature and this isobaric change in volume with temperature. Uh, Now, the problem here is that in order to try and get that change in the internal energy, I first need to figure out this change in volume. And when we do so, it turns out this is actually a really useful property. But because it's going to be a size extensive property, because it's a change, or size extensive property, because it's a change in volume over temperature, we often are going to change this into a size intensive property by just dividing it by the volume. Now, what this will do in practice is it will tell me the relative change in volume as I heat or cool the system. And when we do this, we get a parameter called the expansion coefficient. So this is going to be represented by alpha. And again, this will tell me the relative change in volume as I heat or cool a system. So you can imagine this is going to be a real useful property and is commonly used in a lot of physics applications. Now, as always, we're going to want to check to see what this looks like for our ideal gas or simplified case. Now, in this case, if we're looking at the change in volume, for an ideal gas, I can literally just insert my ideal gas law into here. And so then I'm going to be taking the derivative of the change in temperature of nRT over P. Now, at this point, notice we're holding this system still isobaric. So since we're usually looking at a closed system, moles will be constant, ideal gas law will be constant, or ideal gas constant will be constant, and well, pressure is going to be constant under constant pressure. So we can pull all of that forward out of the derivative, and all that leaves behind is the temperature. And that just gets me the change in temperature over temperature, and as we said previously, well, that's just 1. So that means that this isobaric change in volume is just going to be nR over P. But since we're already looking at an ideal gas system, we can literally just say nRP is just, well, V over T, just by rearranging the ideal gas law. So this gets us an explanation of this isobaric change in volume. So again, that's fairly useful. But again, notice what we actually want is the expansion coefficient. So I can then put in the solution for this derivative into the expansion coefficient. And when I do this, notice we're going to end up with V over T times 1 over V. And when we do this, it turns out our answer is just simply going to be the inverse temperature. Now, this actually has some really fun consequences. Because what it shows is that at very low temperatures, we'd expect a large expansion coefficient, and at very high temperatures, we'd expect a very small one. And the reason why we can explain this is that as I heat a system, if the system is already cold, any additional increase in temperature is going to have a much bigger proportional influence than if it's already very hot. So I'd expect a much bigger expansion going from 1 Kelvin to 2 Kelvin than I would from 300 Kelvin to 301. And so again, this does make a large degree of sense. So what we can then do is make use of this relationship and put it back into our general expression. So now when we do this, we can go ahead and insert in for this derivative by rearranging this v times alpha. So we can determine the isobaric change in internal energy based on our uh, internal pressure, our volume, our expansion coefficient, and our heat capacity. And this equation is going to generally hold for any system, whether it's a gas or liquid or a solid. Again, the big assumption here is we're assuming non-reactive and closed. So we're not allowing the moles of substance to change. But otherwise, this works pretty well. And notice that we can easily measure volume, the expansion coefficient, the heat capacity, and a little bit harder is that isobaric change in internal energy. But all of these can be measured experimentally. So this allows us to figure out uh, the internal pressure as long as we know the difference in between this isobaric and isochoric change in internal energy with temperature. Alternatively, if you're able to obtain our internal pressure, then you can go ahead and figure out this much trickier change in internal energy under isobaric conditions. Now, for an ideal gas, just as a reminder, that internal pressure is going to be zero because, again, the system has no intermolecular forces. And at that point, we'll witness that this whole central term will go ahead and just drop out, and we're simply left with the change in internal energy under isobaric conditions is going to be the same as that under isochoric. So again, this CV is going to be the same as the change in internal energy, which again is going to be a fairly useful relationship. So what we can now do is try and apply the same idea to another parameter, which is known as the isothermal compressibility. So whereas the expansion coefficient looked at the change in volume with temperature under isobaric conditions, at this point we're going to be flipping our variables. And we're now going to look at the change in volume with changing pressure under isothermal conditions. So this would be the idea of if I had isothermal conditions, I apply extra pressure, how much will I compress the volume of the system? And again, very similarly, we want to go ahead and relate this as a ratio. That way we would have a size intensive property instead of a size extensive. But the bigger thing here is now when I increase the pressure, I'd expect the volume to shrink. So we go ahead and throw in this negative sign. And so you can imagine that experimentally, this isothermal compressibility is fairly useful. But we can also use it for a fair number of applications. Most notably, one of the things we can do is relate this to our expansion coefficient using something known as the triple product rule. Because we'll notice that in both cases, we are looking at changes in volume and pressure and temperature. Now, there's a useful thing is if you're looking at the changes of three components, you can go ahead and connect the three of them using something called the triple product rule. So this is the idea in this case. If I'm looking at my isothermal compressibility, the change in volume with pressure under constant temperature, I can go ahead and just rotate these three variables. So rotating them once clockwise, I move the temperature into the changing variable, into the independent variable. I move the pressure into the dependent variable and the volume to the variable being held constant. And then if I do this twice, we end up with three separate partial derivatives. And if I multiply all three of these partial derivatives by each other, I get -1. Now, it is worth noting you can do this same process, but rotating the variables counterclockwise. Either way, the idea is if you sequentially rotate these variables in between three partial derivatives, their product is just simply going to be -1. Well, right now, this is very useful because we know that our isothermal we have our isothermal compressibility, and we also have this guy on the end, which looks rather like our expansion coefficient. And if we go ahead and insert in our expansion coefficient and isothermal compressibility, this means we can get the third one, which is going to be our isochoric change in pressure as I heat. So again, how if I keep a system in a gas in a closed container, I heat it, how much would I expect to increase the pressure? And again, note this will hold for a liquid or a solid because we're now dealing with real systems. Now we like to go ahead and simplify the system a little bit. And so you'll notice we can go ahead and rearrange everything except for this isochoric change onto the other side. But when we do this, we'll notice the negative signs will cancel and that we've also set it up so that our volumes will cancel. And when we do this, this is actually fairly nice because this just simply leaves us behind with our um, uh, our isochoric change in pressure with temperature is simply going to be related to the ratio of the expansion coefficient and the uh, isothermal compressibility. So again, this is a fairly useful mathematical trick we can have in our back pocket as we're now going to be looking at a lot of these complex derivative systems. If I can go ahead and switch what I'm looking at, I can go ahead and get a much harder to determine variable. So again, this is a fairly useful trick that we'll be using from here on out occasionally. So again, one to keep an eye out for. So we can go ahead and with that kind of in our back pocket, which we'll use every so often, we're going to go ahead and re-examine this isothermal compressibility. So again, this is also very nice because anytime you're trying to pressurize a system, knowing how much the volume can change is fairly useful, especially when we're looking at solids and liquids, which aren't going to have those same neat relationships. However, it's always useful to go ahead and first check to see what this looks like for our ideal system, most notably the ideal gas. So for here, we can do a very similar trick that we did last time for the expansion coefficient. So we can take this volume term and insert in our ideal gas law. Now, when we do this, again, note, we're looking at a closed system and it's isothermal. So nRT should all come out in front, and this will just leave us behind with the derivative of 1 over p. Now, this is going to be a little bit more complex than what we saw last time, because now we're taking the derivative not of p, but of 1 over p. Now, if we go ahead, dust off all of our derivatives, we'll note that this will produce an answer of negative 1 over p squared. So when we go ahead and do this, we can also take advantage of the fact that we have a negative nRT over V here. Well, this is an ideal gas. So that's just the pressure. So now I've got the negative pressure times 1 over the negative pressure squared. When we do this, we end up resulting in inverse pressure. So this means the isothermal compressibility for an ideal gas is just inverse pressure. And this will follow a lot of the same logic as for the expansion coefficient. If I've got a very high pressure, I'd expect a very low compressibility, meaning that if I've got a very high pressure and I increase the pressure a little more, the volume won't change much. But if I have a very low pressure, say something like 0.01 bars, and I change it by 0.005, well, now suddenly that's a big percentage difference. So I'd expect a much larger change in volume. So again, we do see in both cases for the expansion coefficient and the isothermal compressibility that we're going to see this inverse relationship, and that will preserve this idea of a proportional change. So now we've got our expansion coefficient, our isothermal compressibility, and we can also look at a couple of other changes, be able to relate it to our final change in uh, pressure and temperature under isochoric conditions. So using this, let's go ahead and take another look at that difference in between CP and CV we talked about previously. So again, we saw this when looking at the ideal scenario that I can go ahead and relate the isobaric and isochoric capacities. And for an ideal gas, this should just simply be N times R. Now let's go ahead and show what this looks like for a real system. Now doing this, we've defined our isobaric heat capacity as the change in enthalpy with temperature, and the isochoric is the change in internal energy with temperature, again under isochoric conditions. Now, what we can do here is go ahead and insert um, our enthalpy term as just the change in internal energy plus PV, as again, our definition of enthalpy. Now, when we do this, we can go ahead and split out that as the change in internal energy with temperature and the change in PV with temperature. Now, when we do this, note that we'll see the cancellation of the first and the third term, leaving just behind that second term. So we'll generally find that the difference in between CP and CV is just going to be the difference, the change in PV over DT, again, under constant pressure. Now, for an ideal gas, we can go ahead and just insert PV equals nRT. So again, we can pull out that nR and we're left with this dt. And lo and behold, we showed exactly what we saw for the ideal system previously, where we can find the difference in between our two heat capacities is just simply nR. And this confirms exactly what we found while looking at the exact energetics for an monatomic and diatomic ideal gas. Again, helping show that it will also hold for any ideal gas, even a larger, more complex system. Now, if we go ahead and examine the system for a general case, it turns out that you can show that this change in PV, this isobaric change in PV with dT, can actually be shown to be related to a ratio of the expansion coefficient squared over the isothermal compressibility. So again, if we're able to obtain these two properties, which are often experimentally determined for a great number of systems, including many solids and liquids, we can look at the difference in between the CP and CV. Now again, looking at this ideal gas case, making sure that we keep getting the same answer every time, which shows the robustness of our equations, we can insert in for the expansion coefficient, the inverse temperature, and for the isothermal compressibility, 1 over P. Now, if we do this, we'll find that we got P times pressure times temperature times volume over temperature squared. Well, at this point, the temperatures will end up canceling out, and you're just left with PV over T, which for an ideal gas is just simply nR. So we've shown three different ways that the difference in between heat capacities for an ideal system is nR. And this really shows that all three of these methods are very consistent, and we've got a lot of robustness in how we treat these systems. Now, next time, we're going to go ahead and keep looking at ideal or at non-ideal systems as we talk about the Joule-Thomson coefficient, and we figure out how we can make these principles useful. Until then, take care.